Okay, guys, welcome back. And as you can see here, today's topic is artificial neural nets. I guess most of you guys heard so many times. And I would say, in AI, I think some guys talking about machine learnings and the other guys talking about deep learnings. And I guess nowadays, if I say AI, most people thinking about deep learnings. Yeah. But like I said, in this semester, I intentionally want to focus on machine learnings, and that's why if you remember all the materials that we covered so far, is like supervised learnings and unsupervised learnings. And that's really depends on whether we have input and associated output or labels or not. And we start with the regressions and the classification. Those are like something related to supervised learnings. And I guess that's the after the midterms, unsupervised learnings, dimension reductions. I think we start with the clustering first and dimension reductions. That's all many topics that we discussed so far. And after that, as you hear, the topic that I want to discuss is artificial neural net. Right? I think this is really critical or important moment that is we are in between. Here is ANN, artificial neural net. Whether this belongs to machine learnings and deep learnings, doesn't matter. It doesn't matter, right? ANN is part of. I really think that this theory is really important. From machine learnings, there is really important transitions from the machine learnings to deep learnings in the conceptual wise. So that's kind of the way that I'm going to explain. So I'm going to here, as you can see, it says I'm going to start with perceptron or logistic regressions video, which are the concept that we already know. We learn in the classifications. And let's move on to, here is MLP is a multi-layer perceptron, same as ANN, artificial neural net. So I'm gonna starting from machine learning, so I'm going to move to multi-layer perceptron or artificial neural net, landing to the beginning of deep learnings. All right. So that's how I'm gonna do for today. So let's see. All right, so the topic is artificial neural net. So in order to, again, I think you guys remember perceptron, that's kind of way back, even before the midterm exams. I think that was the first concept that I introduced when I discussed classification problems. And perceptron is the simplest model that we can think of. So suppose we have this kind of structures. That means that here we do multiplications, right? That's where we're at. We do linear combinations. And in order to induce the non-linearities into the networks, here, I think in the perceptron, we use signed like that. Whether it's a positive, it's going to produce 1. Whether these values are negative, I think its sign is -1. Or you can do step functions as well. It's whether this is output is -1 or 1, or in that case, output is 0, 1. It really depends on how you label them. Okay. And here, just you guys can think of as either sign or step. It doesn't matter, right? But something like had a we have some discontinuities in but it's again it's a nonlinear function. After that, that's predictions out of perceptron in the classification problems. That's how we are supposed to see these networks. And in more like in equation form, in equations or in the matrix or vector form, probably like here, say these are the x and these are the omegas, like coefficient. And basically this is inner product with the constant. Here now is omega naught. I think we're gonna say, from now on, I'm gonna say bias. That's kind of the common terminology in artificial neural net. So it's like, see, it's like any kind of nonlinear functions. That's like something that we learned from perceptron. And here is key thing is how to find out the omegas. The X and true labels for training data set, those are given. Out of those given data set, the solution that we want to find out is omegas. Okay. So omega means the coefficient. This one is kind of something that from like this like the visual like representations, and I'm writing down the equations in the matrix vector form, and also we can geometrically we can draw.
Sorry.
Get,
Professor, I have one question.
Sure.
How do we know the value of y? It's if g of 1 plus 3x1 minus 2x2 is positive, it's equal to 1. And if negative, it's equal to -1, or?
Oh, I see. Okay, see. I see what you got. Let me see. Oh, okay. Let me. Okay, so I'm gonna explain this one, and since we have this one, I'm gonna explain this with your examples, with your questions. Okay. So suppose we have this one. That means this is some kind of sine or step functions. So if this one is, how do I say, if that, it's a classification boundary. Classification that are basically over here, it's a two-dimensional space and everything is a linear, so it's gonna be linear equation. I mean linear classifier or straight line. Having this one, we can separate the entire in 2D space into two. So that's how we do binary classification. Having that binary and linear classifier. Okay. So with that in your mind, I'm gonna say this is omega is give us the information of linear classifier. Linear classifier. Now, how do you suppose we have suppose we have the omegas. Remember, data is given, and out of that, we want to find out the omegas. And after do some kind of calculations and the training or learning process, suppose we got some omegas. After that, if we have new data points here, actually what we did is, actually this is new data points. And what we can do is we do multiplications, right? And since this, suppose this is a step, I mean, sine functions, then we're gonna have minus one. So we know that this data points is negative, and over there is positive. Now the question that you got is whether, so suppose, I mean, how do I say? We do have training data set like that, suppose. And after that, you have to label them. You can label it, I want to label this one is plus and this data point is -1. Or you can label it like this one is -1 and this one is plus. Right? But either way is fine because the classification boundary does not change. And if in let me say this is negative. So in this case, this is how we got. And if that's the actually, if the way that we suppose, I mean, to put it, the labels, and then this is gonna be like I will say -1 and minus x1 plus 2x2. So in that case, in this, label it like the networks. Because we're not gonna decide the omegas, we're gonna find out. So probably this is the way. If everything is working fine, this is the omegas that we're going to find. Okay, is that enough for your questions? And the geometric sense, what I'm gonna do is that you guys remember like omega transpose x, and these omegas x are orthogonal. So in that case, here is the omega is this guy, which means that this is the omega vectors, and again, this is normal, right? And we know that since this is the omega directions, all these plus and minus, or +1 and -1. If you set this one as new omegas, that means minus and +2. So this is in new omegas. In that case, again, it's normal, orthogonal. And here it's gonna be, over there is positive, it's negative. So it really depends on how you labeled your outputs for binary classifications. Either way is fine. Okay, so that's kind of, I use different colors, meaning that this perceptron is gonna split into two subspace. It's basically it's binary, linear binary classifications. That's how we do. Now, from now on, what I want you guys to see is that this part is related to classification boundary. In this case, it's a line, linear equations, linear constraints. Okay. Now let's move to say if we have this kind of networks of perceptron, then means what's the input dimension of the data set? What's the input dimension in this case? Right? You can say on 3D or 2D, but say this is kind of trivial. So I would say it's the input is located in 2D space, two-dimensional space. And if I add more like these circles, like inputs of, I would say unit or neurons, because I'm gonna talk about the artificial neural net, so I would say more neurons here. Then you have to visualize it. Now it's in this perceptron, the input is m-dimensional space, and the omegas gonna represent m-1 hyperplanes in order to split or separate into two regimes. Okay, and this is again, it's mathematical expressions in a vector form. And I think it's just this, I mean, you already learned when you discuss perceptron, so it's kind of recap. Now, as you see the titles, it's from perceptron, I will say multi-layer perceptron or ANN, artificial neural net. Basically, these two are equivalent or identical. As a motivations, there's some famous problems. We call it XOR problems, and you don't have to know what XOR means. Suppose we have four data points like this, and use different colors to represent different labels. And I would say these two data points, the label of them is red, and as opposed to these two are green. Then let me ask you, can we classify or can we separate these four data points using linear classifier? What do you think? We have only four data points. Can we do that? Can we do? We cannot. Let's say we cannot separate it. We cannot separate it. Because since these data points are linearly separable, we have to think about nonlinear classifier. Yes, that's right. So like that. I don't know what, but it's maybe this one is, I think it's okay. It's green and red. That's one way they can do. Or we cannot classify them with one linear classifier. We cannot separate it. Well, but I guess, what do you think? Two linear classifiers like this, I would say, no, yeah, like that. If we have two straight lines, over there it's red, outside it's green, right? So there's two ways that we can think of it for non-linearly separable data points. We can either think about the nonlinear classifiers or increase number of straight lines. In some sense, those are like pretty much they're talking about the same things. Why? Because like in general, suppose we have any kind of functions, and we can approximate it like that. we can approximate like multiple lines. So let's go back to say this. If there's not linearly separable, so we cannot for linear classifiers. So this is obvious. Like obviously, these are the big limitations, and so single neurons, a single is corresponding to one linear classification boundary. So again, it's a nonlinear curve approximated by multiple lines, like what I explained here. For regressions, probably, I don't know, I mean, say it's multiple lines. For nonlinear classifiers, if you think of like that. I guess you guys have kind of basic, the conceptual, the understanding you guys have. Now let's thinking about XOR problems again. Then at least two lines are required. So like, oops, sorry. I think this is good enough. It's good enough. Say we have as two lines. And like I said, in the perceptron, these represent one line where omegas. If you have another perceptron, says omega 1, and these are omega 2. Now we have two lines which represent multiple linear classification boundary. Okay. Now here we have the same inputs and the same labels, and I just draw two perceptron to represent two linear classification boundaries. But we don't have to separate these two because they're gonna share the input and outputs simultaneously. So let's combine them together like this, like that. This is critical moment. It's critical moment. Okay. So that's why we call it, since we have this multi-layer perceptron or artificial neural net. And by looking at this, you have to think about this in your mind, in your brain. And I mean, see here we have three neurons and two neurons, and connected it like that, all of them. But you have to visualize these one linear classifier and another linear classifier. Okay, that's exactly what you're supposed to think or visualize whenever you see this kind of the multi-layer perceptron structure or networks. I'm gonna say there is another adjustment. Remember, like the statement that we have from perceptron to logistic regressions, and the perceptron, the nonlinear function was like this one. We don't like because it's not differentiable somehow. So that's why we want to use this kind of, you guys remember, it's a logistic regression, right? So it's a logistic functions, or we call sigmoid function. So I'm gonna use sigmoid function instead of either step or sine function. So I'm just gonna change it into sigmoid. I think this is always this is totally fine with you guys, because this is the same as the discussion that we had for logistic regressions. Okay, so we call it, this is nonlinear activation functions in the context of ANN, same as sigmoid functions. Now it's differentiable, since we have sigmoid functions like that. Now, if you, okay, this one is the same as the previous one. So here, what we can do more, think about it. So inputs, and we do linear combinations. I mean, linear combination, we do linear combinations and just passing through nonlinear activation functions. And there's nothing between here, so I can combine them together. Now, if you now here, forget about what kind of things inside. And this one is going to be first layer, or is input layers, and second layers. Now that's why for multi-layer perceptron, that's the name is coming from, or we call it artificial neural net. We have layers and second layers, things like that. And each layer has, I would say, unit, or I'm gonna say neurons. And these neurons are connected. And you have to see like these, we have associate omegas on top of the arrows or connections. That's kind of, so from perceptron to multi-layer perceptron. I really hope that you guys can, get some kind of insight or conceptual understanding, strong conceptual understandings. And that's the first way, the one way or a way that you can looking at. And I'm gonna show you another perspective. And it's ANN as a kernel learning. You don't have to, at this moment, you don't have to know what these things. I'm gonna explain it right in a minute. So remember, for linear, let's go back to machine learnings. And for classifications, we start with the linear classifications. And remember, how do you solve the nonlinear classifications? We use kernels. And all the data set we map, using kernels, we map from low dimensional data points in the low dimensional space into data into higher dimensions. And in that case, we're hoping that over there, if we have proper kernels, then we can have the linearly separable data set, like these animations. I think you saw this like a movie clip so many times. So at this moment, you have very strong understanding of linear classifications with a kernel, the concept of kernels. That's really good. And the issue was that if you guys remember it, I said that it's really for nonlinear classifications, the most critical or important thing is how do you find or choose or select the right kernels. That's all we need. That's all we need. But at that time, I said that it used to be really important to get the right kernels But nowadays, it's not like as important as before. And I didn't explain why. I skipped. Remember, I skipped how to find or how to choose the right corners. Why? Because of because of that. Let's see why I did that. And neurons, I mean, basically the circles, or you can think of unit in ANN. That means we do, and this is bias, and these are the omegas. We have nonlinear functions, activation functions. Again, in machine learning and the classifications, remember, like we did like omega naught. Now in ANN or multi-layer perceptron, we just slightly change the notations, like B as a bias and omega transpose X. So that's the notations that I'm going to follow. And here, like omega is, yeah, and Xor problems main weakness is that it's lack, I mean, the linear predictors, a lack of capacity for classifications. All the population has to be linearly separable, but as you know, in more generic or general case, this is a very special case. So to solve nonlinear classification problems, we have to do nonlinear mappings with the function, call it corners. So like that, in one of the examples, say this is corners in two-dimensional space. I'm gonna map it in 2D and 3D space like that. I mean, this is one of the example of corners. In that, now after that, we can do using linear classifier. In this case, it's a hyperplanes in three-dimensional space. Okay, nothing new, you guys already know. See, now let me, suppose that the input is not linearly separable, then what we can do is that, say this is the input, it's not linearly separable. And what we learn in nonlinear classification is, say we have some kind of corner functions, then in this mapped space, now if we have right corners, this is gonna be the linearly separable, right? Over there, we suppose this is non-linearly separable. Over there is linearly separable. And I will say I'm gonna add one more, because in general is from low dimensional to higher dimensions. So it might have more neurons in it, but don't worry about it in that details. I mean, this one is kind of the conceptual wise, kind of the illustrations to help you to have better understanding. So here, suppose the original data set is not linearly separable. So we have to do some kind of corner mappings. And suppose this is linearly, then we can use here, we can use linear classifier. Okay. Now I'm going to show you some of the animations, just focusing on this. The corners, I'm going to change corner to another layers with the neurons, like that. Over there, what we can do is that we can do linear classification, linear combinations with the nonlinear functions. So basically, if we do have, this will be some kind of any kind of functions we can represent. So in the functional wise, this layer is working as a corner. So if you're looking at the titles, you start from corners plus neurons. Over there is neurons and neurons. The first, this neuron is going to work as a corner. Nonlinear mapping can be represented by another neurons or another layers. Okay. Now, just forget about how we came at here, but it's first layers and second layer, third layers, or last layers or outputs. Just layers, we have some neurons and another layers with the neurons and another layers. So this is multi-layer perceptron. Multi-layer perceptron. Okay. So I explain it, ANN or multi-layer perceptron, with two different perspectives. The second perspective was that corners. So in that case, we don't have to define the corners because we're gonna find omegas from data set. That means from data set, the ANN, what the ANN does, find out the right corners and find out the right, I would say, right corners and right classifiers. This one is linear classifier over there. But we do over there in like I would say upstream layers is kind of in the conceptual wise kind of working as a find out the right corners, and like downstreams trying to find out the right linear classifiers based on the features over there, the input. As corner. That's the another way that you can think of. Remember, the first concept was that these are straight line, and this another one. I'm sorry, another one, and we have another one. And from here to here, we have linear mappings, and from there we have another lines like that. So I would say this one is kind of very like microscopic understanding of neural net, and corner is kind of macroscopic way of looking at. I would say both of them are. I mean, it's important to get some insight on artificial neural net or deep learnings, I would say. Okay, so now we can generalize multi-layer perceptron. And two ways of looking at ANN. That is represent lines. So this means that I'm more focusing on the weights over there. And another one is looking at the input and outputs that represent nonlinear relationship between the input and outputs. We have linear combinations. I mean, we do have linear combinations and nonlinear activation functions. So these are just relationship between the input and outputs, or any kind of nonlinear mappings, or any kind of nonlinear functions. Good. And for speaking of nonlinear activate functions, there are many. The only thing they use so far is the sigmoid functions. And we have another one, hyperbolic tangent. And the most famous one nowadays, rectified linear units. We call it ReLU. And we have more. It means like here. We don't have to use sigmoid only. We can use other nonlinear functions. It's totally fine. And if you study more, I mean, there's some pro and cons of sigmoid functions, and there's pro and cons for hyperbolic tangent, and there's another pro and cons for ReLUs. So if you have a right understanding of each nonlinear activation functions, you can decide which activation functions that you're gonna use for your networks and your problems or your applications. Totally fine. But that's kind of something in detail, so I'm not gonna go into that details in this semester, in this lecture, so I'm gonna skip them. But there are many different types of activation functions. Why do we need multi-layers? Let me go back to, okay. Why do we need multi-layers? Input and output. Okay. Linear classifier or linear mappings as a kernel. And if you do like that, so in the original problem, this one was the input and outputs in this. And if you add more layers, now this one is, I mean, it's another input, and this is the output of that. And if that's, so this is kind of typical representation of multi-layer perception or artificial neural net. You have multiple layers, right? And here, this one is the output, and over there, input and outputs. And looking at this, and input and outputs, we do have multiple mappings. Input and outputs. Now, output becomes the input for the downstream layers. And computed, we're gonna generate another outputs. This is gonna becomes another inputs, and we do another linear like mappings and things like that, and eventually we will get outputs. Okay. Summary. ANN or MLP is going to work as a universal function approximator. You can think of it as a regressor or universal function classifier. It's value propagations for that one. And for classifiers, weight. Okay. Now, the last thing that I want to emphasize here is that what's the given in this any kind of problems? Say in this one. Or what's given? Input and outputs are given, at least for training data set. Now, or users have to predefine the structure of neural net. Say I'm gonna have here like how many layers, and each layers how many neurons. That's something that we have to design. Nobody's gonna teach us or tell us. So we have to design. Okay, I will say X and Y for supervised learning case given. And I will say structure. That means that number of layers and number of neurons or units. For this, we have to design what kind of, and after that, out of artificial neural net, the omegas, that's something that from data set, after training, after learnings, the omega is going to be the outputs. I mean, the end, I mean, something that we find out. So these, so suppose you have, you program it in the Python and the given, and this is the structure that you're gonna design it after something. You remember, like in the machine learning, after the training, we will get the omegas out of Python. That omegas, that's something that we have to I mean, this is after the omegas. Now these neural net is working as either this function approximator or function classifier, universal. Okay. So again, we have to find out omegas. We have to find out omegas. That means if you know omegas after learnings, that means that means we don't have to predefine the kernels. ANN is going to tell us based on the data set they have. That's the beauty of ANN. That's the beauty of ANN. But in machine learnings, only thing is that we ask to the machine learning is that find out the classifiers for classification problems, for instance. But in ANN, we're gonna ask to find out the kernels and the classifiers at the same time, only from data set. That's the key. That's the key. I don't have to think about any kernels. I don't have to think about it. Okay. So that's why I said it's parameterized, because the omegas. So another way that we can represent it, x and y, these are the functions, but a function is parameterized. Now this is kind of generic expression of artificial neural net. I mean, neuron is like something like from our brains, and we have some kind of the big insight or ideas from our brains. And basically what we want to do is that we want to find out the function. We want to find out the function approximator between the input and output data. But those relationship in general is going to be very complex, and it's going to be very have nonlinear characteristic on it. Okay. And here in this linear part, and in neurons we have, since nonlinear activation functions, it's going to take care of the nonlinear characteristics. And here you can interpret as feature learnings, kernel learnings, and the classifiers. I mean, I would say we can interpret. And if you add more layers, that means this one has more higher capability of of learning right features or right corners. Since we have the layers, number of layers are increased and very deep, we call it deep artificial neural net or deep learnings. Over there, I have two things that I want to mention. The first thing is that since we have many layers, that means we're gonna have like many nonlinear mappings, right? Then if they say like in input original data set, if you have higher nonlinear characteristics or behaviors, somehow if we have right trainings, then we can find out or we can rearrange it, all the data points or features over there is, we can make it as a data point as linearly separable. We have, this is high capability of representing. Right, that's the one advantage of having deep layers. But on the other hand, we have to think about omegas, number of omegas. We have a lot. We have, I mean, think about it as optimization problems. The decision variables, number of decision variables that we have to find or we have to solve in optimization problems. It's extremely challenging. Right? You have to think about the stabilities and the convergence and so many things that's why, I mean, that's why for deep learnings or like this deep artificial neural net, we need more data set. We need big data set. We have to show many data set to this kind of deep learning models to find out right omegas. I mean, this makes sense, right? I hope that you guys have this kind of big picture of the artificial neural net. Now, based on these explanations or understanding, let's looking at some interesting examples to have to illustrate what we learned so far. Now, I want to looking at the parameters. Basically, I want to look in at omegas. Let's see. So let me see. Okay, let's looking at these examples, and probably if time allows, probably I will switch to the Jupyter notebooks, and I'm gonna do I'm gonna run these examples, but let's see. So if you have this one, again, it's binary classification problems and logistic regression problem. We can solve that as the logistic regression problems, right? And here it's a logistic regression problem. And after we find out the solutions, then let me see. This is the linear classifiers out of logistic regression, which makes sense to us. And before that, let's see, in neural nets, there are some conventions. What is meant by convention is that in Perceptron, we use omega naught. I think I already mentioned it. And now I'm going to switch to B, which represent bias. So it's bias and omegas, okay? And every time we have bias terms. So when you draw something, probably I'm gonna do not indicate the bias unit because we already know. So starting from here, like perceptron, I change to B, and I'm gonna remove it. Although we do have bias neurons. So this is the kind of graphical representation of, right, an ANN, or in this case, the same as logistic regressions. And let me see. Let me see. One hard encodings. I will skip this one, and I will come back. Okay. Okay. See. Let me see. Suppose we got this kind of data points distributed. It's too obvious that this is non-linearly distributed. And I designed my ANS structure like this, my ANS structure like that. And after training, we will get omegas, right? Omegas. So from X and X1, X02, X01, X02. Okay, let me ask, this is really important. How many classifier that we can get out of this structure? How many lines? How many lines? We do have one line and another line. And we will get omegas, right? So with that omegas, we can draw. This is what we got. This is what we got. I don't know which one is that, but these are two lines. Make sense? Okay, this is two lines. And from here, looking at these, and over there is kind of, we did corners. And since over there we have sigmoid functions, and Z1 and Z01 and Z02, the output of sigmoid function is, so here the X is like, these are the range. But if you look, and from 0 to 1 and 0 to 1, since we know that we have sigmoid function in it, okay? And another thing that I want to mention here in X domain, non-linearly separable, and these are working as corners, and I want to see in Z space whether it is after the right corners, whether we is able to make it as transform it as linearly separable or not. And in Z space, it's kind of linearly separable. All the red, all blue are kind of, of course, there's some misclassified data points. It's okay. Everything is, we're talking about the approximations. We want to minimize something. So it's okay to have some kind of outlier, the misclassified data points, totally fine. The thing is that we want to minimize them. So here in Z space, after these mappings, kind of get linearly separable data points. We rearrange them. In G space, we have another omegas, which is again is two lines. Over there is lines. It's linear classifier. Linear classifier. Okay, I would say this example is, I think it's gonna help you a lot to have a right understanding of ANN, to see what kind of things happening inside neural net.
Sorry. How can we choose the Z space? Like, how do we pass from the X to the Z?
Okay, so the question is how we choose it. We don't have to choose. Okay, say we know that the input is x of 1, x of 2. We know that since the input is two-dimensional space, right? So that's only we know that. Output is actually I would say we have single neurons or two neurons, because if you go back, I just kind of skipped one hot encoding. So that one is just, don't worry about, just put them aside right now. And if we do, I would say if we do y1 and y2, and if we design it like that, we know that this is non-linearly separable in the original data point, so we cannot get a right omegas. That means we have to insert another layers. That's the beauty of multi-layer perceptron. And we can add like that. We don't know how many neurons that we're supposed to put it inside. In this example, the reason why they have to put 2, because I want to visualize it. That's the only reason. If I add more, this is going to be 3D space, not 2D, two-dimensional space. So actually, how many neurons do we need to hear and how many layers that we need, nobody knows. It really depends on your experience or your know-how, or sometimes it's try and errors. I mean, just add more layers and seems like it's overfitted, probably then you can get rid of some of the layers and add more neurons and for the specific layers and see if whether it's good enough or not, and try different structures, things like that. Over here, the only reason that I put 2 is that in order to visualize it. Okay. And let me ask, now I have different data. Again, it's binary classifications, but as you can see over there, it's non-linearly distributed. And how many, let me change the problems. So I want to solve these problems using ANN or multi-layer structures, and it's input is like we have x of 1, x of 2, and outputs I will say y of 1, y of 2. So I'm going to add single layers, hidden layers. How many neurons do we need? At least. How many neurons? Or I'm going to say another way. How many lines do we need? How many lines? I'm going to say maybe 4. I think is, so I will try this kind of structures. I will try. So one line, another line, and third lines, and last lines. Over there, we have one lines, but this one is in 4-dimensional space that we cannot draw, we cannot visualize. That's the issues. And actually, and I design it like that and design these kind of structures, and we can compute the omegas after the given training data set after training, although I didn't explain how to train them. Probably the next time I will explain it. And this is what I got. This is what we got. We compute the omegas and we have 4 lines. I draw it and I got this one. First time I thought that was wrong. because the intention that I have was like that. And first, when I said I thought this one is not correct, but after just looking at, I mean, this makes sense, right? 4 lines and separate them. This is kind of over there is some misclarified points, but that's okay. This is another important message that I want to share with you. Original intention that I have, it was like that. And this is what the ANN learned from the data set. That means probably this guy had different corners than me. Which is totally fine. Which is totally fine. This is the good example that some of the advantage or benefit that the for corners is not defined by users. Corner is learned, or features are learned from data set. Okay. Okay, so I think it's at the beginning I said that now we have machine learnings. I mean, for simplicity, I say the machine learnings and deep learnings, we are in the middle. We are in the middle. And I want to focus on how you what's the transition between the machine learnings and deep learnings. In order to explain that way, I start with the perceptrons and what's the geometric meaning of the omegas, and it's related to straight lines. And for non-linearly classification problems, there are 2 ways that we can look at it. The first one is the kernel mappings, and second is the multi-layers, multi-lines, and those are two related. And we did that. And using that, I guess, please, after these lectures, I mean, the examples, I think, first informative. So have that understanding. Probably, I think you guys get good enough to move to the the field of machine learnings. I mean, field of deep learnings. I'm sorry. Okay, so that's all I have for today, and I will stop here. And next time, I think this is I mentioned so many times, and that we're gonna learn omegas from the data set. And actually, I never show you how to train, how to get the omegas, how do you learn the omegas. So here, the next topic is gonna be obvious. It's gonna be how do you find out omegas. We call it training or learnings. That's actually the topics that we're gonna cover it. And okay, so that's all I have for today, and I will